Last Tuesday we finished up section 9.2, which went over stoichiometric equations and how to use them to convert from moles of reactant to moles of product. We started talking about theoretical yield, which is how much product or products you expect in an ideal world where everything runs perfectly. Generally they're reported in grams, sometimes in moles. You guys worked with theoretical yield in experiment 6, what's my formula? When you heated up the salt, the unknown salt, and you tried to figure out what your unknown was by comparing it to the theoretical yields of the 4 types of salt that it could be. If you have questions on the lab, please let me know. It's a really great practice for calculating the theoretical yield of stoichiometric balanced fashion reactions. Those are found in section 9.3, the end of 9.3. And stoichiometric balanced fashion reactions are described as reactions where all of the reactants are used up to make product. So it doesn't matter which reactant you use to calculate your percent yield. In the cases of your lab, there was only one reactant, your starting salt unknown, that you heated, which then decomposed into a lot of products. And you are just using your reactant, the stoichiometric reaction, to convert grams of your unknown into moles, and then moles of your reactant into moles of product, and then moles of product into grams of your salt product. That was calculating theoretical yield of stoichiometric reactions. Section 9.4 in the book describes how to calculate theoretical yield of limiting fashion reactions, which are reactions where not all of the reactants are used up to make the products. So that means it absolutely matters what reactant you choose to calculate theoretical yield. You have to choose what is called the limiting reactant. The theoretical yield, the book gives this example, and it just starts with moles. So unlike your lab, the What's My Formula lab, where you, with the salts and calculating theoretical yield, where you started with grams of your unknown, and you assumed you had grams of each of the reactants and converted it to grams of products. Here, you're just given a balanced chemical equation. You have the moles of the chemical equation, and they're just asking how much product would be made based on this reaction alone, just using the moles of the balanced chemical equation. So for that, all you need to know is you have to have the balanced chemical equation that gives you the moles of each molecule present, and then you calculate the molecular mass, and then using those two values, you can then calculate grams. So you're basically converting your balanced chemical equation from moles into actual gram amounts, and it's telling you that for this reaction, if I react 2.0152 grams of hydrogen gas with 253.810 grams of I2, that will give me 255.826 grams of HI. It's kind of like reading a recipe. If this recipe were in 1 cup plus 2 cups gives me 1 cup plus another cup gives me 2 cups of my product, this might be grams, the metric system instead. So in this case, in stoichiometric reactions, you can just use the moles to figure out your theoretical yield. On the exam, in the questions, I will make sure, and on quizzes, that make it clear whether you're dealing with stoichiometric or limiting fashion reactions. So 9.4. The next section is devoted to theoretical yield of limiting fashion reactions. And you can think of this kind of through this analogy. If we know that we're going to make a sandwich, a cheese sandwich, we know we need 2 pieces of bread, 1 piece of cheese to make 1 sandwich. If I find 10 pieces of bread and 8 pieces of cheese in my kitchen, how many sandwiches can I make? Most of you probably were like, well, you can make 8 sandwiches, obviously, because you got 8 pieces of cheese. True, but let's figure out the logic behind that thinking. The logic that our brains did so quickly that we're probably going to have a hard time describing it. So first, let me go through the logic for bread. If I have 10 pieces of bread in my cupboard, or on the counter, or wherever you keep your bread, I know that for every sandwich I make, I need 2 pieces of bread. I want bread on the bottom because that needs to cancel out. And I want sandwiches on the top. I get 1 sandwich. So just based on pieces of bread that I found, I would get 5 sandwiches. Notice I'm writing the units out all the time. Please write the units all the time. Now for cheese, found 8 pieces of cheese. For every sandwich, I need 1 piece of cheese. And that's going to give me 8 sandwiches. So, in this case, what do you notice? Something that you may or may not have already noticed. The total number of sandwiches that I can make is limited by the number of pieces of bread, even though I have more bread than cheese in the cupboard. It's not going to be 8 sandwiches because I need twice as much bread to cheese. My balanced chemical reaction is giving me the ratio of reactant to product, which is telling me that the limiting factor in my my sandwich making reaction is the amount of bread that I have. So we call cheese, in this case, the limiting reactant. You might also see it called the limiting reagent. And we would call the bread, whoop, nope, said that backwards. We just figured out that the cheese is the excess reactant. We would have 3 pieces of cheese left over and no more bread to make sandwiches with it, while the bread is the limiting reactant. So try now. I want you to write general definitions of limiting reactant and limiting and then excess reactant. So just, we kind of defined it for this specific example, but how would you describe limiting reactant to someone in terms of chemistry? And how would you describe excess reactant? I might describe limiting reactant maybe as the reactant that dictates how much product is made. While excess reactant does not dictate how much product is made. This is in terms of products. We could also say maybe the excess reactant and then I want each of us to compare to book definitions and change your definition as needed. Please do this so you have accurate definitions. But it's good for you to try and process this information on your own and then add to it as you learn new information or get more detailed information. Alright, so now we know that in some reactions there are limiting reactants, and we need to figure out what those are. So let's practice determining theoretical yield with limiting fashion reactions. And remember, consider your molecular equation that is balanced as a conversion machine that only accepts moles. It'll accept moles in either direction, but it's got to be moles. So if we have 2 moles of C3H8 or propane and 2 moles of oxygen and we mix them together, how many moles of CO2 will we get? So if we're determining the limiting reactant, or the LR, we're going to do the same thing we did with our bread and cheese analogy. I had to convert the bread and the cheese into sandwiches to figure out which one is the limiting reagent. So I have to convert the propane and the oxygen into product to figure out which one is limiting. 2 moles of C3H8 if I'm converting moles of C3H8 into moles of product of CO2. Well, I gotta look at my balanced chemical equation to convert moles to moles. So I'm gonna put moles of C3H8 on the bottom because I want those to cancel, and I want to end up with moles of CO2. So those have to go on the top. If I look at my conversion from the balanced chemical equation, I see there's 3 moles of CO2 produced for every 5 moles of oxygen used. Oops, sorry, 5 moles of propane. 1 mole of propane. Jeez. Right here. 1 mole of C3H8 for 3 moles of CO2. If I do the math, 2 times 3, it'll give me 6 moles of CO2. If I do the same thing for oxygen, for every 2 moles, so for 2 moles, for every 5 moles of oxygen, I want oxygen to cancel. I would get out 3 moles of carbon dioxide. Two times 3 is 6. 6 divided by 5. So we had 6 moles of carbon dioxide from 2 moles of propane and 1.2 moles of CO2 from 2 moles of O2. Second step in this is we have to use the limiting reactant, which is oxygen. So if we use the limiting reactant to determine the theoretical moles of product, we get 1.2 moles of CO2. Now what if we wanted to determine the grams of product? Well, we'd have to take our moles of product and convert it into grams. And what relates moles to grams is always going to be the molar mass. So I'm going to have 1 mole of CO2 on the bottom, and then I need to calculate the molar mass of carbon using the periodic table. It should be about 44 grams per mole. So 44, I got 0.009 grams for every mole of CO2. and multiply those together, that's going to give me the grams, because the moles of CO2 are going to cancel. I have to go by least number of sig figs. 2 sig figs and 1.2, so that's 53 grams of CO2 produced for theoretical yield in an ideal world. So I want you to try it. If we have 10.0 grams of propane and 10.0 grams of oxygen, what is the theoretical yield of CO2 in grams? So step 1, determine the limiting reactant and use that balanced chemical equation. If you want to pause the video now and try it, please do so. I highly recommend that you do before you continue on. So this one has a little bit of an extra step. We're given grams now instead of moles. So I now need to convert using the molar mass of propane into moles of propane, because our chemical equation only ever accepts moles. So if I use the molar mass, then I get moles. Now I can use my balanced chemical equation. I know for every 1 mole of C3H8, I get 3 moles of CO2. And that's going to give me moles. So grams of C3H8 cancel, moles of C3H8 cancel. We need to calculate the molar mass of C3H8. So that's 12.011 times 3 plus 8 times the molar mass of hydrogen. That's 44.097. Now I can do the math. Oh, that should be 44.097 grams. $10.0 divided by 44.097 times 3. .680. I should have 3 sig figs. Moles of CO2. For O2, if I start with 10 grams of O2, times the molar mass of O2, so that's 31.0 Ch988 grams of O2 for every mole of O2. And then I use the balanced chemical equation. Moles of O2 are on the bottom to cancel. I want moles of CO2 on the top. Moles of CO2 are 3, and the moles of oxygen are 5. Again, grams of O2 cancel, moles of O2 cancel. Now I can do the math. 10.0 divided by 31.9988 times 3 divided by 5. And again, lowest sig figs are these. Remember, the balanced chemical equations, those are exact numbers. So it should be 3, so it's 0.188 moles of CO2. So again, and it makes sense, oxygen should still be the limiting reactant because we are using the same chemical equation as above. The second step we're going to want to do is convert our limiting reactant into grams. 0.188 moles of CO2. Step 2, convert it to grams. What relates moles to grams? The molar mass. Oops, that should be moles. So we need moles on the bottom, grams on the top. Mole CO2 cancels moles of CO2. I'm left with grams, which is what I want. Now I need to calculate the molar mass of CO2, which we have calculated previously and found to be 44.009. And that's going to give us 8.27. Again, least number of sig figs comes from the moles of CO2. So that's 8.27 grams of CO2 could theoretically be made if we started with 10 grams of oxygen, which is the limiting reactant. So if I reacted 10 grams of propane with 10 grams of oxygen in the lab, and I actually only recovered 6.98 grams of CO2, what is my percent yield? Percent yield is comparing what you actually got, how close or far away is it to your theoretical yield. So you have to divide your actual yield by your theoretical yield and multiply it by 100, and that's going to give us 6.98 grams CO2. My theoretical yield, which I just calculated, times 100, 6.98 divided by 8.27, 84%. We'll say for sig figs, 84.4%. It's decent. That's a decent yield. If you get the closer you get 70 and below, your yield isn't great. Depends on what reaction you're doing, though. So list 2 reasons that the actual yield would be less than the theoretical yield. If you want to pause the video here, take a second, write down some answers. There could be many more than 2, so I recommend asking some friends what they got. I would say one of the main reasons could be spelling incorrect, weighing of material, in this case we're dealing with gases, so maybe leaking or escaping gases. So maybe you did make it, but your product escaped out of the container. Maybe you spilled some. Other reasons, maybe it evaporated. Maybe your reaction didn't actually go to completion. You need to react it longer. But if you have questions like this on the lab, I want you to be as specific as possible and just try and think of all of the ways. It's human error is a big part, but just writing human error tells us nothing. Did it leak? Was it a gas? Did it leak out somewhere? Did you not fill a syringe correctly, potentially? Did you spill reagent? And also it could be that you didn't run the reaction for long enough, so maybe it's you, but also the reaction itself didn't go to completion. Maybe your equipment wasn't working properly. There's a lot of reasons. Let's try and be specific. So that was theoretical yield calculations with a limiting reactant. You can definitely practice more of those in your homework. Go through this video again and let me know if you have questions. We're going to move on to section 9.5. The main takeaway of this section that talks about combustion analysis, I won't be testing you on combustion analysis. It's just a method in lab that lets you determine the mass percent of atoms in a chemical formula. So I want to focus on using mass percent data and calculating mass percent data in conjunction with empirical formulas to determine molecular formulas. So you guys have seen molecular formulas already, you've predicted them. Things like C5H10O5, N2O, those are molecular formulas. We haven't talked about empirical formulas yet. And we talked very briefly about mass percent data way back in chapter, I think, 3. And I told you to hold off because we come back to it, so we're coming back to it. So empirical formulas versus molecular formulas. Molecular formulas you've seen a lot of. It's the actual formulas you've been working with. Molecular formulas are exact. They tell you exactly how much of each element is present in the molecule. Empirical formulas tell you ratios. And they're only whole number ratios. So similar to the Scottish shortbread example that we did, where I said it's 750 grams of flour to 500 grams of butter to 250 grams of sugar. That's an exact recipe to make 60 cookies. 375 grams of flour, 250 grams of butter, and 125 grams of sugar is an exact recipe to make 30 cookies. What these each have in common is the ratio of flour to butter and sugar, which is 3 to 2 to 1. So the ratio of each ingredient would be similar to an empirical formula compared to a molecular formula. So Ch2O, these are ratios of carbons to hydrogens to oxygens in molecules. The actual molecular formulas have the same ratio, 6 to 12 to 6. If you divide everything by 6, that's a 1 to 2 to 1. 10 to 20 to 10, if you divide everything by 10, that's a 1 to 2 to 1 ratio of carbons, hydrogens, and oxygens. So we're going to use these empirical formulas to figure out some percentages. I'm going to list out the steps, walk you through some of the steps, and then you can practice one on your own. I will not go over the practice problem right now, but you can ask me questions if you have questions. So an example, we have a compound containing carbon, hydrogen, and oxygen. It is 55.1% carbon and 8.1% hydrogen. What is its empirical formula? So we can use these percents to figure out the empirical formulas. First, whenever you're given these problems, assume you're starting with 100 grams of compound and you're going to convert the percentages into grams. So I have some grams of carbon per 100 grams of compound times 100 should give me the 55.1% of carbon in this molecule. If I do the math, I'm going to divide by 100 on both sides. That's going to turn 55.1% into 0.551. Multiply by 100 to get on both sides, and now I get 55.1 grams of carbon in every 100 grams of compound. I can do the same procedure for hydrogen. Instead of this equation equaling 55.1%, it's going to equal 8.10%. Now for oxygen, it's a little bit different. So the setup for hydrogen would be this, and I would need to solve for the question mark. For oxygen, however, you first need to figure out the percentage, because we're only given percentages of carbon and hydrogen. But we know that this all has to equal 100% of the compound. So if I add the percentages of carbon and hydrogen together, and then I subtract that number from 100, that's going to give me the percent of oxygen. So 100% of the compound, which is 55.1% plus 8.01%. .8% hydrogen, oxygen. Oh, no. Oh, not O2. So we're talking about elements. We're not talking about gases or molecules. So it's just 36.8% of oxygen. And then I can set up the same formula that I did for carbon and hydrogen to get the grams of oxygen. And I should get the same, because we're working with 100%, we should get the same grams as the percentages. Step 2, you convert the grams you just got into moles. That's, again, grams are related to moles through the molar mass. And we just have the element carbon, so it's 55.1 grams times the molar mass of carbon, 1 mole on top, 12.01 grams on the bottom. Do the same for hydrogen and the same for oxygen. Oxygen is going to be 36.8 grams of oxygen times 15.999 grams of oxygen on the bottom to moles of oxygen on the top. That's going to give us 2.30 moles of oxygen. Right, now we have our moles. If the moles that we calculated are not whole numbers, then we're going to divide by the smallest number of moles. Because remember, we're looking for that ratio, and we need ratios in whole numbers. Smallest number of moles was oxygen. Divide everything by 2.30. Oxygen's now a whole number 1. Hydrogen becomes 3.48. Carbon becomes 1.99. Now you can move on to step 4, which is the rounding rule. You can, or the multiplying by integers of 2, 3, 4, increasing until you get numbers you can round. Now the rounding rule for mole subscripts in a empirical formula is you can only round up if the number is within 0.1 of the next whole number. So 3.48 is definitely greater than 0.1 away from 4. If you don't believe me, put 4 minus 3.48 in the calculator. You'll get 0.52. 1.99 . So because this isn't, one of them is not within 0.1, we're going to multiply before we round. So let's start by multiplying with 2. Hopefully that's enough. In this case it is, so we can stop. 7 minus, so if I multiply these by 2, now oxygen is 2, hydrogen is 6.96, carbon is 3.98. Now I'm going to check 7 minus 6.96, 0.04. That's within 0.1 of 7, so I could round that one. And carbon is 3.98. That's 0.02. That is also within 0.1. So now we can round, which is step 5. Sometimes you don't have to do step 4 if you're already at a point where you can round up here. So now I can round and I get C4H7O2, and this is the empirical formula. You're done. This is the ratio of carbons to hydrogens and oxygens for this compound that has the mass percents that we were given. And that's it. So we just did a problem going from the percentages of elements, the mass percents given, using that to find the empirical formula. This is a problem where we want to find the molar mass of a we want to find the molecular formula. So we have the molar mass of the compound, and we have the empirical formula. So we know the molar mass of the compound is 173 grams per mole. If you want to take a second and just write out the rest of what we know and what we're trying to find, if you want to pause the video right now. The other thing we know is the molar mass of our empirical formula. We can calculate it. And I get 87.09 grams per mole. So this is molecular formula. This is empirical. And we actually want to know the molecular formula of a compound that weighs 173 grams per mole. The other thing I know is that the empirical formula shows the ratio of elements, while the molecular formula is exact. For a specific compound. So we can actually figure out if this is a ratio compared to this. That would mean that their molar masses should also give us ratios. Figuring out what we're trying to figure out here is the molar mass of your empirical formula is related to the molar mass of the actual compound by some whole number, right? Because if this is a ratio of how many carbons, then this is just some version of the ratio of your empirical formula. So if I take my masses and I divide them by one another, I have the molecular over the empirical. That gives me 1.98, which I can round up to 2. This is the factor to multiply the empirical formula by. To get the molecular formula. So if I take C4H7O2 and I multiply all those things times 2, that gives me C8 H14O4. It's the molecular formula. So if you have the molar mass of the molecular formula and you have the empirical formula, you can compare those two molar masses. You get the factor out that you need to multiply your empirical formula by to get your actual molecular formula. So here, I want you guys to try a similar problem. Pause the video, take as long as you need to, then you can come back and watch the rest of this. So this question's asking, the lab determines the percent composition by mass of a compound is 82.7% carbon and 17.3% hydrogen. Part A, what is the empirical formula? Part B, if a compound made of C's, carbons and H's has a molar mass of 145.35 grams per mole, what would its molecular formula be? So we gotta go back and use all those steps for part A. So one, we're gonna assume we have 100 grams of compound and convert the percentages to grams. So grams of carbon we have 100 grams of compound times 100 should equal 82.7% carbon. And then 17.3% hydrogen, which should be 17.3 grams of hydrogen. Then I can convert these grams of hydrogen and grams of carbon into moles using their molar masses. Periodic table, I want grams on the bottom. 94 grams of H, moles of H, .011 grams of carbon, 1 mole of carbon. That gives me moles, and then we're done with step 2. 82.7 divided by 12.011, 6.89 grams of carbon. Moles, should be moles, because my unit on top is moles. And then 17.3 divided by 1.00794 gives me 17.2 moles of hydrogen. Okay, so we are pretty far from the rounding rule. Okay. So now I'm going to put that into our empirical formula and we divide by the lowest number. So this here is step 1, and this right here is step 2. Now I'm at step 3. I have C 6.89, H 17.2, and if I divide 17.2 6.89 gives me 1 carbon, which I'm not going to write. You don't have to write the subscript 1. And it gives me 2.50 if I follow sig figs for carbon, for hydrogen. We can't round. 2.5 is 0.5 away from 3. That's too far. So we have to do the multiplication step, which is step 4. So here we'll do step 4. Let's try multiplying by 2. So step 4. And that's gonna give me C2, H 5, and we're good. So luckily we didn't have to keep multiplying because we are now at exactly whole numbers. And this is our empirical formula. Part B asks, so we have to use the empirical formula that we're given, and if we have a compound that has some number of carbons and some number of hydrogens with a molar mass of 145.35 grams per mole. We also have our empirical formula, so I know I have to do this divided by the empirical formula molar mass, which we have to calculate. And we get 29.062 grams per mole. And then this is the C5C2H5 molar mass. That should give me the ratio that I need. 145.35. 5.001, which is approximately 5. Multiply this by 5, that gives me C10, H25. And you're done. The last section we're going to talk about, so we just talked about how to go from percent composition given, finding the empirical formula, and then finding the molecular formula. Now we're going to just go from the molecular formula to the percent composition. I'm going to go through the guidelines. It's a much shorter process. And again, if this looks daunting, please just practice. The more practice you do, the more it'll become muscle memory, and you'll actually understand what's happening, because you have to organize your thinking as you write. So now we're going to go from a molecular formula to a percent composition. For these guidelines, Step 1, you assume you have 1 mole of your compound to start with, and you determine the grams of each element. So we're trying to find the percent composition of carbon, hydrogen, oxygen in the molecular formula C6H12O6. If I assume I have 1 mole of C6H12O6, 1 mole of that contains 6 moles of carbon from the subscript. I need to put moles of my molecule on the bottom and moles of carbon on the top, so I just get moles of carbon out. And then I can convert the moles to grams using the molar mass of carbon. So do the same thing right now if you want to pause the video for hydrogen and oxygen, and then you can continue the video once you're done. So 12 moles of hydrogen to grams. So if I'm assuming 1 mole of my compound, I would have 12 moles of hydrogen. It's the same as up here. I just didn't show it. And then if I have 1 mole of the compound, I would get 6 moles. So you can use your molecular formula to just tell you how many moles of each thing. And then we'll find the grams of hydrogen. So moles of H, grams of H, 1.00794, and then 15.9994 grams of moles of oxygen. Moles of oxygen cancel there, moles of hydrogen cancel there, and I'm left with grams, and I get 11 point okay, 11.9 and then 6 times 15. 9 is 95.994. And so now we can take all of these and add them together. 72.06 plus 11.90594 plus 95.994 grams of oxygen. Okay, so I think here you use a different periodic table, but according to the periodic table I'm using now, I get 179 point, and then this should go out to the 2 decimal places, 9.6 grams. Now, step 3. So step 2 is just determining the entire mass of the compound. You add all the masses up. Step 3 is determine percent mass for each element. Percent of carbon, I take the mass of carbon that I calculated, divide it by the entire mass, multiply it by 100. For hydrogen, I take the mass of hydrogen that I calculated, divide it by the entire mass of the molecule, which here we said is 179.96 grams, 179.96 grams, C6H12O6. And for oxygen, that is 95.994 grams oxygen divided by 179.96 grams C6H12O6. And your answers here are just arbitrarily rounded to the hundredths place for step 3 only. So here I get 40.04%. 40.04% carbon. And then 4 divided by 179.6 100. Here I get 6.62% hydrogen. And here I get 53.34% oxygen. And then the last step, step 4, so right down here, you add all them up. And it should equal roughly 100%. I got exactly 100%, which is awesome. But sometimes you might get 99.99 or 99.98%. And the last thing, I want you to try this one. So pause the video, take a second to try this, and then come back and you can see the answer after you've attempted it. This is just trying what we just went through. So what are the mass percents for the elements in the following compounds? We'll do caffeine in light blue. So I have 8 moles of carbon from the empirical formula. I need to convert that to moles to grams of carbon. And I'll say the steps, but I'm gonna write them out in a line. So if I convert moles of carbon into grams, I need the molar mass. Cross out my units, that's going to give me grams of carbon. Step 2, determine the mass of the entire compound. So first, let me take this guy, and then for 10 moles of hydrogen, 4 moles of nitrogen. And nitrogen is 14.0067 grams nitrogen. And then 2 moles oxygen, that's 15.999. Oops, that should go on top. 15.999 grams of oxygen per mole of oxygen. Moles are canceling in oxygen, moles are canceling in nitrogen, and moles are canceling in hydrogen. So do the calculation. 8 times 12.011 gives me 96.088 grams carbon. And then 10 times this will give me, move that over 1, 10.0794 grams hydrogen. And then 14.0067 times 4 will give me 56.0234. 6 grams of nitrogen. .998 grams oxygen. Step 2, so this is step 1. Step 2 is I add all this up. And I get 194 point. The least certain tie between carbon and oxygen, so we go out to the thousandths place right now. 192 grams of CH10N4O2. So notice in these steps, step 1 and step 2, in finding the mass, you're actually finding the molar mass and multiplying it by 1 mole. It's another way you could think about it. Finding the molar mass of the given compound and multiplying it by 1 mole. We're assuming we have 1 mole, figuring out the molar mass of each element, and then adding them all up. It's 2 ways to do the same thing. That's done. Step 3, determine percent mass. So now we have the molar mass of the whole compound, and I'm going to take each one of these and divide it by so for carbon, I take 12.011 grams of carbon divided by the molar mass. I'm going to show this as an example. And note that I am doing the same thing for the other elements, but I'm just not showing it. So for hydrogen, it would be grams of hydrogen. So the 1.00794 on top divided by the molar mass times 100. .19 So remember, here, this is where we arbitrarily round to the hundredths place for the percents. For hydrogen, that's 1.00794 divided by 194.192 times 100. We got 0.52%. Nitrogen would be 14.0067 divided by 194.192 times 100. That's 7.21%. And finally, the percent oxygen would be 15.999 divided by 194. Oh no. What am I doing wrong? I'm taking the masses of each element. I need the mass that I calculated, not the molar mass. That's why these numbers are so low. It's looking strange. So this is why it's helpful also to write out your problems and write out the units so you have a paper trail. So if you're accidentally pulling the wrong numbers, it will eventually become apparent and you can look back and see what's happening. So the carbon should be 96.088, what we calculated for the mass of carbon in this compound. It's going to give me a much higher number, which will make a lot more sense because there's a lot of carbon in here. And carbon weighs a decent amount. So that is 49.48%. Hydrogen is 10.0794 divided by 194.192. 5.19%. Nitrogen is 56.0268 divided by 194.192 times 100, that's 28.85%. And then oxygen is 31.998 divided by 194.192 times 100, that's 16.48%. And the last step, add all percents together. So 16.48% from oxygen, 28.85 from nitrogen, plus 49.48 from carbon, plus 5.19 from hydrogen, and I get exactly 100%. Alright, thank you for following along. Do part B, ask me questions in class, and I will see you all on Tuesday.